Assalamu alaikum warahmatullah. Today we will continue our discussion about linear independence and basis. Now consider a vector space of V. Okay, so in this vector space V we have a set of vectors from x1 to x sub k. Now we can have the following form. For every vector V in the space V capital, say, we can represent this vector by a linear combination of the above vectors now. So this set of vectors, they are special. Okay, now this is called linear combination, right? And we'll talk about those vectors in a bit now. Okay, now any set of vectors are called linearly independent if and only if we form a linear combination, and this linear combination will equal the all zero vector. Okay, so it's all zeros, right? If and only if all the multipliers, which are scalars, equal to 0. Okay, so if we can find such a special set of vectors that are linearly independent, we can deduce the following. Any set can be either independent or dependent. Okay, if any vector in this set is 0, then of course this set is dependent, of course, because we can find a non-zero lambda such that when you multiply it with the 0 vector, you will get this statement. Okay, now if the set is dependent, then at least one of those vectors in this set can be represented by the other vectors. So one vector is dependent on the rest of the vectors, at least one, of course. Okay, now the interesting part. If we stack those vectors in a matrix A here, right? How do we know that this set of vectors, they are independent or not? We stack them in a matrix A, perform Gaussian elimination until we reach the row echelon form or reduced row echelon form. Okay, then only the vectors that corresponds to pivots, they are independent vectors. Otherwise, so if the pivot is 0, if we don't have pivot in that column, this means that this vector is dependent on the other vectors. Okay, so in general, if we have a vector space V, when we say vector space, meaning that we have a set V of vectors that we have two operations defined on that set: vector addition and scalar multiplication. And we have a set of vectors that belong to this vector space V. Okay, then any vector V in that space can be represented by linear combination. Remember, now we can put those vectors in a matrix A, or in that subset of vectors that can also be called a matrix, so we can call it a generating set. Okay, now the set of all linear combinations of A, meaning we go back to equation 130 here, so any linear combination of those vectors, this is called the span of the set or the span of the matrix. So we can write in two forms: the span of the set of vectors, so we mention the vectors, or the span of the matrix A. Okay, this set or matrix A is called minimal if there exists no smaller set, meaning there's no less number of vectors that can span V. So such set, meaning the minimal set, is called the basis. So a basis is a minimal generating set. What is a generating set? It's a vectors that, using the linear combination, we can span part of the vector space. Okay, for example, the standard and the canonical basis of R3, which is the 3D space, is this set of vectors, right? So this is 1 0 0. Let's say that this is in the x direction, this is in the y direction, and this is in the z direction. Okay, this is not a unique set, meaning that we can find other bases for the same space or vector space. For example, this one here. Now we can check that those vectors, they are bases. How? Form the matrix B here, right? 1 0 0 1 1 0 1 1 1. Okay, and perform Gauss elimination. In fact, we don't need to perform Gauss elimination because we have already. We can see that this is a pivot, this is a pivot, this is a pivot. So we have 3 non-zero pivots, meaning that those columns, they are linear independent, meaning that they constitute a basis for R3. Okay. Okay. Now we have this example here, right? So A belongs to which space? Let's make it a bit thicker. A here belongs to which space? R to the power 5 cross 4, right? Now we have to make a distinction now. Okay, those vectors, we have 4 columns. They span this vector space. So if we call them, this is A1, A2, A3, and A4. So we can say that, let's write it here, the span of A, which is the span the vectors A1, A2, A3, A4, this belongs to the vector space. Okay, are those vectors bases? No. Are they generating set? Yes. Okay, again, what is a basis? It's a minimal generating set, meaning we need to find the independent vectors from this set only. How to do that? We can perform Gauss elimination to reach the row echelon form. We can see that here we have a 0. This means that this vector is not independent, so A3 is dependent on the other vectors. So we can reduce the set to contain only the columns 1, 2, and 4. Okay, so just let me be clear here. So this is A belongs to 5 cross 4, but here it's sorry, the span of the vector belongs to R5. So what does this mean? Okay, so when you have a generating set, right? So let's say that we have this vector V that is a linear combination from I equals 1 to let's take the original generating set, 5 lambda I a sub I, right? So those are vectors, of course. Okay, so what is the resulting value? It's a vector. Okay, what is the dimension of vector V? It should be the same dimension of vector A. What is the dimension of vector A? You count the elements of vector A, which is what? 1, 2, 3, 4, 5. So the vectors A here, they belong to the vector space R to the power 5. So is the vector V, and hence the span of A. Okay, so we can say the set of vectors B, they span R5. Okay. Okay. Just before going there, so let's just take a break here and talk about how do we connect this thing to linear algebra. Okay. So we were talking about vector spaces, then vectors. Then now we said, okay, we have a set of vectors and we put them in a matrix like this one here, right? Okay. So now we are talking about matrices. And if you remember from a previous video, we said that the column space of A is a subspace. The column space of A is a subspace. And A can be a transformation. It can be a system. So we are interested in A and in its column space as well. So now let us prove that A is a column space. So A is a column space. The column space of A is a subspace of R of to the power m. Okay, this means that the column space A is a subset because a subspace is a subset of Rm, let's say. Okay, so how to prove that? First of all, we need to prove that the subspace, or this candidate, let's say, subspace, is closed under vector addition and scalar multiplication, and then we need to prove that the all zero vector belongs to that set or candidate subspace. Okay, that's very simple to do actually. Let's say that we have two vectors that belong to the column space of A. What does this mean when we say two vectors that belong to the column space of A? This means that U and V can be represented by A times any vector x, let's say x1, and V, it would be A times x2. Okay, so this is the definition of a column space, which is any vector that is the results of A being multiplied by another vector. Okay, now let's take the addition. So we plug in the definition here, take A out, and call this new vector x1 plus x2 x3, and this by definition it belongs to the column space of A. So we have proved that the vector addition is closed in this column space, or candidate column space. Now we need to prove that the scalar multiplication is closed as well, which is very simple. So we define a vector in the column space of A, then we will multiply it by some constant C. Here C should belong to the to R, which is scalar, right? Multiply it, okay, then take the C inside. Now define a new vector Y, okay. Y still belongs to Rm, and this is by the definition again, this belongs to the column space. Now Z is very simple, the all zero vector is very simple. Okay, again, can we find a vector x that is multiplied by A that will give us the all zero vector? Yes, it is the all zero vector again. So the all zero vector is in the column space of A, meaning now this last condition is satisfied, so we can say that the column space of A is a subspace of Rm. Okay, now again we need to talk about the dimension. So A is a matrix that belongs to the Rm cross n space. Okay, sorry, I think I need to do I need to correct this thing here. Yeah, right. The column space of A is a vector that belongs to the Rm. Okay, the dimension of the column space is the number of independent, okay, columns. This is columns of A, which is the same as the rank of A. Okay, So let's get back to the notes here and return to this bit. Okay, now let's say that we have a basis set, right? If the order of the basis is important, we call this ordered basis. Okay, and this is important. Why? So we can define what is known as the coordinates. The coordinates. So now here we have a generating set, and we have x here, which is the linear combination of the b's. Now the alphas here, they are called the coordinates of x, and the order of the coordinates is important. So if we defined, let's say, defined a point in the 3D space, so this is x, y, and z. So we have this point here, right? So this point is here. This is our point. So it has coordinate x node, which is in the x direction, y node, which is in the y direction, and z node, which is in the z direction, right? So the ordering of the points or the coordinates is important because it will tell you in which direction you should move, or where to find your point. An example, let's say that we have a standard basis, okay, and we have x is in r squared. So what are the standard bases here? E1, let's say x direction, E2 in the y direction, okay. Now x equals 2e1 minus e2, right? Okay, this means that we can say it's 2 times 1 0 minus 0 1. We can put those coefficients 2 and minus 1 in a vector here and stack the bases in a matrix, and we have this form, a matrix form, right? Another example here, we can have the same point or the same vector represented by different bases. So we have this point here, which is which one? Sorry, this x in R2 that is represented by the standard vectors here as this point here, right? We have the basis vectors E1 and E2, and we can have different basis set B1 and B2 with the same vector, and you expect to have different coordinates. So for the first case it was 2 and 3. When we're using vectors B1, which is 1 minus 1, and B2, which is 1 1, we have different set of coordinates, minus 0.5 and minus and plus 2.5. Okay.